So we're looking at the solubility rules today. This is the primary thing that we're looking at. And when we look at the solubility rules, what I want you to think about is I want you to kind of look at these solubility rules kind of as like a layer cake. And what I mean by that is there are some rules that are kind of the foundation of our understanding of solubility. These are rules that do not change, that are structurally sound, that do not have exceptions to them. And so we'll bring them up. There are two rules in particular, one dealing with cations, one dealing with anions. And the wonderful thing about this base is that it's exception free. I don't have to worry about any extra stuff kind of showing up because it's not going to. Now, we'll get into some rules after this that aren't as straightforward and have more exceptions to it. But this is a solid foundation. So the first half of this base is the cation rule. And the cation rule states this. These cations, those found in group 1A, so all of your alkali metal cations, and the ammonium ion, NH4+, those are always soluble in water. Always soluble in water. So it doesn't matter what they are paired with, they are going to dissolve in water as ionic compounds. And from this, you can understand why when we do a lot of things in lab, if we pull a solution off the shelf, the chemical formulas for most of those things are sodium salts or potassium salts. Reason for that, they're inexpensive and we know they dissolve in water. So that's the cation rule. Cation rule says if I've got an alkali metal ion, group 1 ion, or the ammonium ion, that substance is going to dissolve in water. The other half of our base is the anion groups rule, rule number 2. This concerns the anions that are always soluble in water. And we're looking particularly at 3. Nitrate ions, perchlorate ions, and acetate ions. These ions always dissolve in water. And again, it doesn't matter what they're paired up with. So again, think about when we interact with stuff in the laboratory. If I've got a copper solution, that copper solution is usually copper 2 nitrate. Why nitrate? Because nitrates dissolve in water. So that's the basis that we're going to build most of our understanding of solubility on. If I see one of these kinds of compounds present, I know it's going to dissolve in water. And I don't have to worry about, oh, well, is this one of the exceptions or is this one of the normal ones? It doesn't matter. It always behaves the same way. And that's what's wonderful about these particular ions. There's no crossing over, no exceptions. Exceptions come in for others. And so your book gives you a solubility table that looks over this. The solubility table largely falls under a couple of big idea umbrellas. So solubility. The 2 types of things that we are most concerned with in terms of solubility are halide ions and sulfate ions. Halide ions are usually soluble. Sulfate ions are usually soluble, but there are some exceptions in both cases. Now, to avoid being the science teacher that says, okay, the best way to learn this stuff is just to memorize it from a big old list, that's not the best way to learn things. Anybody will tell you that. Now, there are some things, unfortunately, you have to memorize because there's really no other way to do it. But in this case, we do have a couple of things that we can use that do help with helping us remember what the exceptions are. So the exception here for the halides, the silver ion, the mercury 1 ion, and the lead 2 ion. I've seen two different acronyms used for this. One of them is happy. So if I take the H from the mercury, the A from the silver, and the P from the lead, I can draw out the word happy here to describe the exceptions to the halide rule. Halides are soluble unless they're happy. Now, it's okay, but it's a little bit clunky just because you've got all those extra letters in there, so it doesn't really spell happy. It just kind of does if you capitalize the first letters. So it's okay. You know, you can think about the happy halides. The other one, the one that I learned when I was a student, also kind of forced, but it kind of takes advantage of the elements' names instead of their formulas, is good old Merle. Merle's chlorides do not dissolve. What are Merle's chlorides? Well, Mer refers to mercury, L refers to lead, and S refers to silver. So it's a little less disjointed because you don't have as many letters in between. Who is Merle? I don't know. Doesn't matter. I still remember Merle's chlorides 25 years later, if that makes any difference. So I'm not saying these are perfect. They're corny. But sometimes corny is what it takes. So that's the halides. For the sulfates, I'm going to add another sulfate to this list because it's in your solubility chart. In addition to these, the calcium ion also tends to behave this way as well. If you go on to take Chem 106, what you'll find is the term solubility and what we describe as being soluble or insoluble is a matter of relativity rather than absolutism. Everything is insoluble at some point. It's just a matter of when is that insoluble point? How much do I have to add to the water so that it doesn't dissolve anymore? And so there's a cutoff point that exists between what we would call a soluble salt and an insoluble salt. Calcium tends to walk that line. And so sometimes you see it included, sometimes you see it not included. That's why. Now, my tortured example here for what we're going to call a way to remember it Balcomer sulfates will not dissolve. What are the Balcomer sulfates? Barium, lead, calcium, mercury, and the S this time isn't silver, but rather strontium. And so sometimes I have been known to put an R here on the end, even though it doesn't say Balcomers anymore, just to kind of remind myself that the S there isn't silver, because the S is silver in the other one. One thing that you should notice, though, there is a little bit of common thread here. The mercury 1 ion and the lead 2 ion are on both lists. And they're both on both lists because they just tend to form compounds that don't dissolve well. And so the only times where we see these kinds of compounds dissolving on a consistent basis are with kind of your standard bottom of the cake ions, nitrates, acetates, chlorates, so on. Now, the good news is those are the hard exceptions. On the insoluble side, excuse me. On the insoluble side, the exceptions generally tend to fall on the bottom of that cake. Meaning the ones that are soluble are the ones that are always soluble anyway. So for carbonates and sulfides and hydroxides and phosphates and pretty much any other ion that you can think of that isn't on this list, you'll find that they're always soluble with group 1 cations and ammonium. And the reason why they're always soluble with group 1 cations and ammonium is because everything that bonds with a group 1 cation or ammonium ion dissolves in water. That's why it's the bottom of the cake. That's why it's that base. The only exceptions here are the exceptions related to, there are a couple of heavy alkaline earth metal ions that will dissolve some of these basic ions. So sulfides tend to be basic, and we'll find that calcium and barium and strontium will dissolve them. Hydroxides are the kind of the telltale mark of a base, and calcium, barium, and strontium will dissolve those also. And when they're dissolved, we know from our discussion on Wednesday, those bases that form are strong bases. So not only do they dissolve, they dissociate very well when they dissolve. They make strong electrolytes. But those are the solubility rules. So again, the big idea is that if I know that I have an ion that is soluble all the time, I know that whatever it's attached to is going to be soluble as a salt. After that, it breaks down into, we have things that usually dissolve and things that usually don't dissolve. A solubility table helps with that, but here's the thing. You're going to have to learn how to evaluate this without a solubility table. And so part of the next couple of proficiencies is kind of prepping you for that. And so when we start looking at this assignment, we start looking at this assignment, the next couple of assignments are going to be geared at giving you enough practice, enough exposure to these ions, that at some point you aren't going to need the table unless you're just really stuck. And so the thing is, we know that other ions exist beyond these. If we come across an ion that isn't on these tables, we can pretty safely assume that it behaves on this side, the insoluble side, and that the only exceptions that exist are the common exceptions, the group ones and ammonium. Otherwise, they'd be on this table. But here we're kind of focusing on the most common aspects. All right, any questions before we move on? Okay, with all of this in mind, rather simple question here. Which of these compounds is soluble in water? Now you can only choose one answer. So consider that carefully as you make your choice. Go ahead and put in an answer when you've got it. So right away, your eyes, excuse me, right away, your eyes should have been drawn to one of these answers immediately. Anytime you have a problem like this, first thing that you should look for is one of those always kinds of ions. And so the only one up here that is an always ion is rubidium. Rubidium, Rb, is in group 1. Group 1 ions always dissolve in water. So right away, we know C is correct. Doesn't matter that it's a carbonate and that carbonates are usually insoluble. Rubidium always dissolves, end of story. Now it comes down to the other ones there. Am I going to choose C or am I going to choose D, since I can only choose one answer? And what I need to look at is, okay, lead and silver, they don't have rules associated with them. I've got to look at the chloride, I've got to look at the sulfate. Now, chloride and sulfate both fit on that usually soluble list. However, chlorides are part of the halide family. Halides are soluble unless happy. Happy, the A in happy is silver, the Ag. So that's one of the exceptions. Is lead part of the Balcomer sulfates? Yeah, that's the L in Balcomer. So in both cases, A and B identify exceptions to the rules. And so only C would be the correct answer here. Any questions with this one? Okay, so our last task for this week is we're going to kind of set the table for how we use these solubility rules to predict reactions. But before we can get into the prediction part and the way that we can kind of systematically show the reaction taking place, we need to identify the reactions themselves so that we can learn to identify them. And the most common type of reaction that works in this kind of way is the precipitation reaction. A precipitation reaction is simply a double replacement reaction where we are starting with two solutions. So aqueous here, again, means that that substance is dissolved in water. So I've got two solutions that I'm bringing together, and the result of those solutions being brought together is a solid compound. That solid compound is known as a precipitate. And that's why these are called precipitation reactions. They generate precipitates, they generate solids. Now, how do I know that these are soluble and that this is not? Well, other than just being told that the reactants are soluble, I need to follow on my solubility rules. My solubility rules tell me, okay, hold on, I've got nitrate ion. Nitrates are always soluble, so that one dissolves in water. I've got sodium chloride. Sodium always dissolves in water, so that one's going to be aqueous. On the product side, sodium nitrate, I've got a double always. Sodium is always soluble, and nitrate's always soluble. And so with silver chloride, by elimination, if I put those together, I get this white solid. That has to be the white solid. But even if I didn't know that, I would still be able to look, okay, the chloride rule, chlorides are halides, Merle's mercury, lead, silver. Okay, silver's one of them. That's one of my exceptions. Now, precipitation reactions are kind of the primary driver here. But what we'll notice is that in addition to precipitation reactions, we also have other reactions that are similarly constructed to precipitation reactions, but don't necessarily give us a solid. So a close cousin of the precipitation reaction is the neutralization reaction. The neutralization reaction involves the reaction of an acid and a base to create an ionic compound and water. Now, what do they have in common with the precipitation reactions? They're all double replacement. In each of these cases, I'm seeing the cations switching partners to make new products. Copper switches places with sodium. I get sodium nitrate and copper 2 hydroxide. Hydrogen switches places with sodium. I get sodium chloride and water. Lead switches places with potassium. I get lead 2 iodide and potassium nitrate. All of these are double replacement. What makes them stand out? What makes them different? Well, in a neutralization reaction, instead of getting a solid product, I'm getting a liquid product. The liquid product, we can almost think about as being a liquid precipitate, water here. Not something that we visually can see, but if you had lab yesterday in room 301 and you did that titration, we can still monitor the progress of that reaction using indicators. pH changes do take place in these reactions, and we can see through changes in pH fluctuation whether or not a reaction is occurring. And that's the whole basis of what a titration does. All right, let's walk through this one together. So here we're looking at barium chloride reacting with ammonium sulfate. So this is a double replacement reaction. So I've got barium chloride, which we're told is aqueous. And if we didn't know that already, barium is not one of the exceptions to the halide rule. So halides are usually soluble and barium does not accept that. So it is soluble as well. And we've got ammonium sulfate. Also aqueous because they tell us. Also aqueous because ammonium compounds are always aqueous. Now, the thing that we have to remember here is that this is double replacement. So I'm seeing the barium changing places with the ammonium ion. Now, the thing with double replacement reactions that we have to take stock of is the fact that even though we are making different compounds, the charges are not changing. And so one of the places where some of you went wrong this afternoon on the proficiency was you didn't know how to handle the different subscripts when they existed. So from the periodic table, we know that the charge on barium is +2. We know that the charge on the chloride is -1. If we did not know from our polyatomic ions that the sulfate is -2 and that the ammonium is +1, there is a trick that we can use. If you remember, when we talked about the concept of taking charges and crossing them over to make subscripts when they don't agree, we can reverse that concept when trying to figure out charges. So the subscript of 2 here tells us that the sulfate charge must be -2. The lack of subscript on the sulfate tells us that the charge on the ammonium is +1. And so now when we're creating our products, I know that the barium goes with the sulfate. The barium was +2. The sulfate was -2. The charges match, so I don't do anything. I leave it right there. For the ammonium, ammonium was +1. Chloride is -1. The charges match, so I don't do anything. And so, yes, this comes out to a balancing issue where if I had to balance this, I would need a 2 there to balance out the ammoniums and the chlorides. The question is, which one of these is the solid? Well, I know from my solubility rules, the ammonium compound can't be the solid. Ammonium compounds always dissolve in water. So the ammonium chloride is going to be aqueous. The solid here must be the barium sulfate. And I can prove that, again, using our solubility table. Sulfates are usually soluble, except for the Balcomer sulfates. And what is the Ba in Balcomer? Well, it's the barium. So barium is the exception there to the rule. And so now that I've got the chemical formulas correct, I would need to put that answer in. Since I can't put in subscripts, I would just write out the formula exactly as it's shown there on the board. BaSO4. All right, any questions here? So this is kind of where we're going from here. Now, there are a couple of other examples. We already talked about neutralization reactions. The other kind of close cousin to this is the gas-forming reaction. And in the gas-forming reaction, what we see is a double replacement reaction that generates a gaseous subproduct instead of a liquid or a solid. But they all have the same kind of common features, the same common family. They're double displacement reactions, just kind of done up a little bit differently at the end. Where we're going on Monday is we're going to take a look at the idea that the way that we've been drawing out these chemical equations thus far hasn't been a truly accurate picture of what's actually going on in those solutions. And the reason we know it's not accurate is because we already know from what we talked about with dissolving things that those ions break apart from each other. but that equation doesn't show that. So on Monday, I'm going to talk to you about how to show that ionic character. And yes, it looks very complicated and sloppy, but it does actually help us to understand what's going on inside of that solution just a little bit better. So on your way out, make sure that you hit that stoplight question and have a great weekend. I'll see you on Monday.